Start recording. Well, last time we discussed the rotating closed loop in the constant magnetic field, in the uniform constant magnetic field, and well, if we open the book, yes, last time we discussed this situation, and last time we discussed this situation and the final electric motive force that we derived was equal to number of turns in our coil or in our loop, doesn't matter, multiplied by B0 of magnetic field, magnetic flux density, multiplied by omega, which is the rotational speed of our contour, and multiplied by sine omega t. Okay, if we look to this device is clearly AC generator or alternating current generator, and the electric motive force is directly proportional to the angular velocity, magnetic flux density, and also sorry, here I skip one one term, NB0S omega sine omega t. Well, we said this is the alternating current generator, and the electric motive force is directly proportional to the number of turns, to the magnetic flux density, also to the surface S, and also to the angular velocity of our loop. And when you design the AC generator, you design according to your needs. You may change velocity, angular velocity, or magnetic flux density, or etc. And in most cases you need constant you need constant frequency. That's why the angular velocity also will be constant, and you change in order to change the value of EMF, you may change number of turns, or magnetic flux density, or area of the loop. Well, now let's discuss another case, which is more general case of this one, where you have a rotating loop and also time varying magnetic field. if we go to the book, to our book, so here okay. Well, here we have the again a loop rotating with the angular velocity of omega 1, and the magnetic flux density also changing in time as uh, changing as sinusoidal b0 multiplied sine omega 2 t. What will be the electric motive force in this case? So total electric motive force, we have already said that total electric motive force in such cases will be the sum of motional electric motive force plus transformer action electric motive force. Well, motional action electric motive force is equal from our previous problem is equal to this n multiplied by b s omega sine omega t is equal to okay, angular velocity omega 1 multiplied number of turns multiplied the area of the loop and multiplied the b, which is here is given as b0 sine omega 2 t and multiplied sine omega t, which is in our case sine omega 2t, sorry, omega 1, because this is the omega 1 shows the angular velocity of our contour, and omega 2 is the rate of change of our magnetic flux density. And transformer effect electric motive force is equal to minus n df over dt. Okay, let's go to the new page. Let me write here transformer action electric motive force. We said minus n dphi over dt. It will be equal to minus n multiplied by s cosine omega 1 t multiplied dB over dt. Okay, and B, in our case, B is given as B0 sine omega 2 t, and the derivative of b with respect to time is equal to the derivative of sine is cosine, which is omega 2 b0 cosine omega 2 t. And if we put this expression here, transformer action electric motive force will be equal to minus omega 2 n s b0 multiplied by cosine omega 1 t multiplied by cosine omega 2 t minus omega 2 n s b0 cosine omega 2 t cosine omega 1 t. Okay, and the total electric motive force we said will be the sum of two contributions. Total electric motive force will be first contribution is omega 1 s n b0 sine omega 1 t sine omega 2 t plus second contribution is minus omega 2 n s b0 cosine omega 1 cosine omega 2 minus omega 2 s n b0 cosine omega 2 t sorry, let's write omega 1 t cosine omega 2 t. Okay, this is the general expression for electric motive force when you have a rotating closed loop inside the time varying magnetic field. Your loop is rotating with angular velocity of omega 1, and the magnetic flux density is changing with the frequency of omega 2. Okay, and if we want to simplify further, for example, if you design your device such that omega 1 will be equal to omega 2, which is omega, the final electric motive force will be omega multiplied s n b0 cosine 2 omega t with minus here. Okay. In the upper red box you have equation for general case, and in the lower green box you have equation for particular case when omega 1 and omega 2 are equal. Your electric motive force will be minus, here we have minus omega s and b0 cosine 2 omega t. Okay. So for now, do you have questions or no? Not yet. Okay, not yet questions, and let's go on and let's see one problem. Okay, here is our book. We go on and okay. Sorry. Copy. Paste here. So the problem is saying a simple AC generator is made by inserting a loop of radius d equal to 50 millimeters inside a long solenoid of radius b equal to 60 millimeters. A number of turns per unit length of the solenoid is unequal to 1000 turns per meter, and this carry a DC current equal to 1 ampere. The loop is connected to the outside and provided with an axis to rotate as shown in figure 10.10. Okay, as shown in picture. First, if the loop rotates at 300 rotations per minute, calculate the electric motive force in the loop. Let's start with the first question. Well, the first question is looks like the problem which we solved in the previous lectures, and which we called EMF, electric motive force, due to the motional action, or in other words, you have a constant magnetic field B, and inside this constant magnetic field you have a moving loop. However, using this approach, using approach where EMF was equal to integral over the closed path V cross B dr. This approach will be much more complicated because our loop is in the form of circle, and we need to define this dot product for each point of circle, that or we need to do one more integration. I think it will be a bit difficult. That's why we use the approach. Anyway, if we use any approach, we will get the same result. That's why we will use more easier approach, d phi over dt. So first of all, the flux density inside the solenoid is constant, and it can be calculated by using Ampere's law. And after, when we compute the flux density B, we can find phi, magnetic flux, and after that we can find electric motive force. Okay, let's take into account this contour with the width of W, and according to Ampere's law, B multiplied W should be equal to mu 0 N multiplied by I multiplied by W, where N is the so-called turns per unit length, and multiplied by width gives you the total number of turns. That's why we write N by W. And from this equation we find that B, magnetic flux density B, will be equal to mu 0 N multiplied by I. Okay, mu 0 is constant magnetic permeability of empty space, which is 4p multiplied 10 to minus 7 multiplied N is 1000 turns per meter, and I, the current flowing through our solenoid, is 1 ampere, and this will be equal to, okay, 10 to minus 4, it means 0.004 0.0004 pi. The magnetic flux density inside our solenoid is 0.0004 p Tesla. And now we can compute the magnetic flux crossing our surface, magnetic flux crossing our loop or area of our loop. And phi, magnetic flux, we know, was equal to integral over the S BDS, and it will be equal to b multiplied by s multiplied by cosine alpha. This is in Weber. And alpha here, the alpha is the rotation angle at rotation angle of our closed loop at some time, and alpha is equal here to rotational speed of our loop by time, and we get phi equal to b as cosine omega t, and df over dt, which is, so let me write from the beginning, and electric motive force is equal to minus df over dt, and which is equal to minus d bs cosine omega t over dt. And if we take the derivative with respect to time, we get what? Minus omega bs, sorry, bs, with derivative of cosine is minus sine, so it will be plus sine omega t. Omega multiplied by b multiplied by s sine omega t. And if we want to compute the numerical values of our if we want to compute the numeric value, electric motive force will be equal, we said, omega bs sine omega t. Well, omega is given. We are given that our loop is rotating 33,000 rpm, and from here omega will be omega will be 2 pn over 60. Yep, it should be like this. Okay, 2p multiplied 3000 over 30 is equal to, so 30 and 30 simplifies, 100p, or if 100p we have 314 radians per second. Okay, we found omega, we know b, we need to find s, which is p r squared, area of our circular loop is equal pr squared, which is 3.14, or better, let's write P multiplied R in our case is 50 millimeters, 0.05 squared. Okay, we put all the numeric values in our equation of EMF. Equal omega, we found 314 multiplied. B was equal to 0.0004 P multiplied. S is equal to this one, to P multiplied 0.05 square multiplied sine omega t, sine omega t. So if we multiply
minus bo'ladimi ustoz shu yerda?
no, why minus?
Minus emasmidi o'zi boshida?
Minus qisqardi.
Ha, qisqardimi?
Kosinusdan hosil olgan payti qisqaradi.
Ha, bo'ldi.
0.0004 multiplied 314 multiplied 314 multiplied 0.05 multiplied 0.05. Okay, what we have? EMF equal to 0.0031 sine omega t volts. Okay, for now is everything clear until now? Okay, and let's move to the second part of our problem. Second part is saying, if the loop is made of a copper wire and the wire has a diameter of 1 millimeter, calculate the maximum current the loop can supply, shorted output. Neglect the resistance of wires leading to the loop. The conductivity of copper is 5.7 10 to 7 Siemens per meter. Okay. So, second part of our problem. If the loop is made of copper wire and the wire has a diameter of 1 millimeter, calculate the maximum current the loop can supply, shorts output. Neglect resistance of wires leading to the loop. In other words, if our loop, okay, let me show you the picture here. In other words, if in this case, if our loop is made of copper wire, you may look here also. If our loop is made of copper wire, how much electric current can flow through our loop in this case. Well, in order to find the current flowing through our loop, first of all we need to find the resistance of our loop, and after that with the help of Ohm's law we can find the current. Okay, the resistance is given as L over sigma multiplied S, where sigma is the conductivity of copper. This is sigma, and length of copper is equal to 2p, and the radius of our loop is given as small d, 2p d divided by sigma multiplied, and the surface of cross section of our wire is p. The diameter is 1 for the, that's why d over 2 squared, and what we have, p and p simplifies to d over sigma d over 2 squared, which is, okay, 2 multiplied 0.05 over sigma 5.7 10 to 7 multiplied 10 to minus 3 over 2 squared. Well, we are out of time in Zoom, that's why let's reconnect to the conference. I will pause the well, let's continue. If we compute the numeric value for the resistance, it will be 0.007 ohm. And now we can compute the current flowing through the loop. Current will be equal to electric motive force over resistance. Electric motive force was equal to was equal to 3.1 10 to minus 3 over the resistance is 0.007, and this is equal to ampere. Okay, it means that the device which we have discussed here in this problem is AC generator, alternating current generator. Because here pay attention, here we found maximum current that can supply our device, because we took the maximum value of electric motive force. In general, our electric motive force was alternating. Here we can see electric motive force here in general is alternating as sinusoid. Okay, this device is can be here we the device here we discussed is can be thought as AC generator that can supply peak current of 0.443 ampere, and which operates at peak voltage of 3.1 millivolts, and the frequency of alternating current is 50 Hertz. So there is also third part of our problem. The third part is saying how much energy must be expended in rotating the loop in 1 hour if the terminals of the loop are shorted. Okay. To calculate the energy, first we need to calculate the power, and then if we multiply power by time, we can find the amount of energy which should be expended in rotating the loop in 1 hour. And okay, the power from the Ohm's law is equal to pay attention in AC currents. Okay, we are dealing with AC current. In AC current, the power will while calculating the power, we use effective value of current, effective value of electric motive force. So I effective is I over square root of 2, and the power is equal to I effective squared multiplied by R. Or if we replace, power will be I squared multiplied by R over 2. I in our case is 0.443, 0.443 443 squared. The resistance is 0.007 over 2, and power is equal to, so it is a very little value, 0.443 multiplied 0.443 multiplied by 0.007 divided by 2 is equal to 6 point, so 6.87 10 to minus 1 2 3 4 minus 4. So in order to not to, okay, this is the, well, this is the power required to rotate our loop in these conditions, and the energy which is required to rotate our device for 1 hour is equal to power multiplied by T, where the power is 6.87 10 to minus 4 multiplied T, 1 hour is 3,600 seconds, and this is equal 0.06 2.47 joules. Okay. So, do you have any questions or any problems? So if you don't have questions, please have a rest for 5 or 10 minutes, and after we will continue. So I will stop the video.